All right, so visual search tasks. In these kinds of tasks, participants examine a display and then they judge whether a particular target is present or not. So they might be shown something like this, and they're asked to find the circle that has a plus sign in it. Or they might be shown this, and they might be asked to find the one that doesn't have a plus sign in it. It turns out it's easier to find the one circle that has a plus sign in it than it is to find the one that's missing the feature. And these are simple examples that I'm showing you. There's lots of different kinds of visual search tasks with different kinds of added in or subtracted out kinds of contexts. Typically, people are faster at finding an added feature than they are at finding a missing feature in a field full of targets that have the feature included. So let me show you another example. Here we have a bunch of red spots. The orange spot is red with yellow added into it, right? So finding an orange spot in a field of red, that should be an added feature. Well, it turns out people are faster at that than they are at finding the red spot in a field of orange. Now, of course, we're on a screen and other kinds of things that may be impacting how red or orange the things are looking to you. You might say, oh, I'm seeing the red faster on the left panel than I'm seeing the orange on the right panel. Across several trials and lots of different illuminations and lots of different contexts, people are faster on average at finding an orange spot or its type of thing, right? It could be a purple spot in a field of blues. It could be a green spot in a field of yellows. It's easier to find that than it is to find the one that's missing something, right? We've removed the yellow and now we're left with the red. It's easier to find something that has an added feature than it is to find something that has a missing feature. And this really supports the idea that feature analysis is separate from the step where you detect the features and then combine them together, right? This kind of supports that analysis by synthesis model idea that it's a three-stage process. So this kind of design helps to illustrate aspects of that theory. I just thought I'd throw this in. I don't know if this is entirely as relevant as it could be, but searching for targets when there aren't that many targets to be detected, right? So when you're searching for something that doesn't always happen, and in fact maybe rarely occurs. So here we have, I'm going to show you a picture. Okay, here we have a scan from the airport, right, TSA, and you're looking to see if this, I said gun or no gun, but it could be knife or some kind of weapon. There's a weapon in that thing or not. You're not readily seeing it, so you have to really look. Whereas in this one, if it's gun or no gun, it's a lot easier to make the judgment when the target is present than when it's absent. And that makes a lot of sense, doesn't it? So, if you're looking for guns and you see a gun, you can stop looking. If you're looking for guns and you don't see a gun, that doesn't mean that there isn't one. You know that you need to keep searching. It's possibly hiding, or it maybe is disguised or something like that. So we find that people have faster reaction time when they're searching a field for a target and the target's there than if they're searching a field and it's not there. And I think it's because they're like double checking and making sure. Here's another example where the radiologist is searching for evidence of lung cancer. And lung cancer typically is going to take the form of white shapes that are usually very bright on the background and usually not the kinds of roundish shapes that you're seeing here. And so they know what they're looking for, and they know that what they're looking for is white. And so they have to look for it. They have to really scan all the different white things here to look for evidence of the lung cancer. So researchers impose a little gorilla. See it up there in the upper the upper right corner of the picture. You can see a little gorilla there superimposed over the lung tissue. And they reported how many, I can't remember what the total number was, but a majority of radiologists didn't see the gorilla in the lung tissue. In fact, nope, I didn't get the reference for you. I thought when I saw the study, thank God they didn't find the gorilla. I mean, if lung cancers sometimes present as black objects, I guess I should be expecting them to see gorillas more because they should be looking for black things. But because it tends to show up as a white thing, it doesn't make a lot of sense to be searching for anything that's black. You should be searching for things that are white. And yeah, you might have noticed that there's a gorilla there, and like, why is there a gorilla on this lung scan? but that's not what you should be searching for. We should be searching for white things. And in fact, in the absence of those white things, I'm really drilling down and making sure that I haven't overlooked a white thing. And so, and in fact, when they first reported this, they're like, you know, radiologists aren't noticing the gorillas. They've now subsequently developed computer software that you can have, you know, sort of as your double checker. Computer software overlooks things too, but you can program it to look for certain kinds of things, and sometimes it'll pick up things that the humans didn't pick up because it was like small or too close to something else, and so the computer might pick it up. The computer didn't pick up the gorillas either because it wasn't programmed to look for gorillas. The human wasn't programmed to look for gorillas. So when we're searching for targets, if we know what we're looking for, we will in fact ignore and literally not even see things that aren't part of what I'm searching for. Have you ever, let's give you an example where you were searching for a target. Have you ever been looking for something and you're like, I can't find X. Where is X? Why can't I find X? And somebody tells you it's up on the right-hand shelf, and you're standing right there, you're looking at the right-hand shelf, you're like, I do not see it. It is not here. And then the person comes marching in and smugly shows you, there it is, it's right here in front of your face. You're like, how could I not have seen that? Well, the way that you didn't see that is that maybe it didn't look the way you expected it to. Maybe it was turned around and the label looks a lot different from the back than it does from the front. Maybe the size was different than you were expecting, right? Maybe there was something about it that didn't fit your prototype of what you were searching for. So not to give you an excuse, but as a person, my entire life, my mom would tell me that, you know, I'm the world's worst looker. I would just like to point out, sometimes it's because it doesn't look the way you're expecting it to look. I'm looking for what I'm looking for. I'm not looking for all the varieties of things it could be, right? So that's my defense. All right. So let's take a little segue into word recognition. Reading is really just a series of word recognitions, isn't it? You recognize the constellation of letters and it produces a word, right? So I got some data out of Jacoby and Dallas from 1981 and factors that influence how quickly and how accurately you recognize words. High frequency words that you're familiar with, you tend to recognize better than low frequency words, even if you're familiar with them, right? But frequency implies how often are likely to have been exposed to it. So some words are very high frequency words, like the and, right? Like these are very high frequency words, and you tend to see them a lot, and people tend to recognize them very quickly. Even if they're in a different font, or even if the background is not that distinct from the actual font. So maybe you've got blue font on a gray background, so it's not that distinct, you still can recognize it because those are high frequency words and you're used to them. Low frequency words, on the other hand, are words that aren't very common, that you don't see very often. So for example, on our slide, we have the word autobiographical. You don't see that as often. People tend to be poorer at recognizing words that they don't see as often. And it might be because we have to stop and we have to sound them out. We have to do other kinds of things to try and figure out what that word is, right? Priming, I mentioned priming earlier, if we get you in that mindset to be thinking about a particular thing. So if you have been primed, those are the right-hand bars in each side of that picture, so the purple bar and the red bar. So you were primed to already be thinking about the subject that word is related to. You see better recognition than if you are unprimed. And that would be the turquoise and the green bars. But you'll notice that green bar is way smaller than the other bars, don't you? Those are unprimed. This is a condition when you aren't primed to be thinking about these, this topic, and low frequency words. So words that you don't see that often and that you were not primed to be thinking in that train of thought about, you get that poor performance that you see over in panel A, right, with the low frequency words. I mean, so it's exactly the same level. So if we prime you, low frequency words, suddenly you recognize them just as well as you do high frequency words, if we prime you and get you thinking about that. So that's another factor, is whether you're already thinking in that train of thought, right? And then finally, context, right? One big powerful context to recognizing letters is if those letters are combined into a coherent word. You will recognize the letters better if they are part of a word than if they are presented individually. And so that's what you see in this picture, where the green bar is where the letters are just being presented one by one, and you're supposed to name them, and they're out of order. All of us can name our alphabet really fast if it's in order, right? A, B, C, D, E, F, G. But if you have an A followed by an X followed by an L and like that, and you're hopping around, you have a moment where it takes you a second to utter it, and you may even start to mispronounce. You might say what you were expecting to come up, and so you can have more errors. Whereas if it's a letter within an entire word, you're going to be better at recognizing it and maybe recalling it separately. You'll remember that you saw the word the, and then you'll say, yes, there was an E in it, right? Like that is an easier process than just by itself remembering that an E had been on the list. And so context is really important, and words provide really profound context. All right, now feature nets and word recognition. Okay, so here's a series of features, right? And you have feature detectors in your brain, as we've already talked about. So letters are made up of a bunch of different features. Here we have a bunch of different curves and lines and different features that might be present in a word. Those features get combined into individual letters, right? So you put together different combinations of features and you end up with our letters. We then have bigram detectors, which is combinations of two letters together. You'll notice there's a little repetition here, right? We have CL, and then we also have LO, because they're bigrams. You have to kind of combine them into two letters. And then finally, you have the word detector, when it comes all together and you can detect that entire word. Each detector has its own activation level, its own point at which it'll start to respond. With input, this activation level increases, which means that with input, as you're reading or you're hearing words or you're seeing them on the screen or whatever, it takes more stimulus for your brain to respond. That's what, and whenever activation level increases, that means the threshold has increased. It takes more for you to respond. Some detectors are naturally easier to activate. Some are like ready to respond. Others take a little bit more convincing to start to respond. Detectors are going to fire when their response threshold is reached. And we find the threshold is higher when that particular detector has recently fired, right? So if you already just processed a word that had an O in it, there may be a little beat where the detectors involved in responding to an O have to get it together to be able to respond again. And then frequency of firing. So if you, let's say this entire list that you're being presented with contains, every word has an O in it, that frequency, the fact that it's over and over and over being used can have an impact on the threshold and make it a little bit slower. So this kind of goes back to the handwriting example I gave you, and also when the forms are exactly the same. We call those ambiguous inputs. Here's a different version of an ambiguous input where the letter H and the letter A are written exactly the same, right? So we have this phrase that says the cat, but it also kind of looks like it says Thai cat, doesn't it? Or in this case, CQRN is not a word, but it kind of looks like a word, doesn't it? It's kind of close. Let's focus on that one, CQRN, as our stimulus input. You may actually display what's called a recognition error for this non-word by imposing well-primed detectors. So if we've been talking about things that relate to a real word that is kind of formed like this one, you may already be thinking in a particular route, a different area. If recently you've been primed with that, or frequently you've been primed with that, so you've got this bias in your network to possibly respond to certain kinds of inputs in ways that are consistent with the ways that you've responded with those inputs in the past. It can cause errors, and sometimes we find those super funny when we have like what we call spoonerisms, where you switch the first letters of two words in a row. There's a classic one that they attribute to, oh my God, I can't think of his name. Winston Churchill, where he says he'd rather have a bottle in front of me than a frontal lobotomy. That's kind of a little spoonerism that he did on purpose, kind of thing, where you mix those letters. Those kinds of little mistakes that we make, those are errors. But think about it from another argument. Here we have CQRN. We've got these feature detectors being activated and bigram detectors being activated. And then your brain goes, I think it means corn. I think they were trying to write corn. Think about how forgiving our brain has to be when sometimes stuff is written in handwriting, sometimes a sign is broken. Sometimes you think how forgiving your brain needs to be. So the fact that you might have an input that looks like CQRN and you interpret it as CORN and make it into a real word, that's a lot more efficient than you saying, I don't know what that says. I don't know what to make of that. And, context is indicating it might be corn. We just previously had been talking about going down to the farm stand and buying some corn. We're in the context of the farm stand and there's ears of corn laying there, and yet you say, I don't know, that sign says CQRN. I don't know what they're selling here. Think how maladaptive that would be. So being able to guess, it tends to help us more than it hurts us. And I'd really I'm going to reiterate, I told you the entire class, I keep saying, we would rather be quick than right. We'd rather be efficient than accurate when we are making cognitions of any sort. A lot of the times when we're wrong, they really were selling CQRN. Well, that doesn't really impact your life. You're like, well, I don't want any CQRN. I was hoping you had corn. Doesn't really impact your life. They're like, where's the punishment? Maybe they didn't really have corn. Usually it doesn't harm us to make these mistakes. What does potentially harm us is if we miss an opportunity as a result of us being too rigid and needing things to look exactly the way they need to look in order for us to respond to it. And so, if you duck because you think something's coming towards your face and you don't want to get hit, that's maybe there's a tiny bit of embarrassment involved, maybe. Or maybe you ducked so fast that you hit your head on the way down or something like that. Maybe something remotely bad might have happened. But if you don't duck, and it turns out it really was something being thrown towards your head, you can imagine that's a bigger risk, right? You had a chance to miss it, but your brain said, it doesn't look exactly like a ball coming towards my face, so I'm not going to duck, right? So more often it helps than it hurts to have these recognition errors. All right, let's go ahead and stop here, and we'll come back and talk about the McClelland and Rumelhart model in the next video.